Okay, Quantum Mechanics 2020, University of Toronto. This is lecture about perturbation theory of Feynman diagram, perturbation theory and Feynman diagrams. Okay, so I'm going to explain this pretty slowly because I'm pretty sure that most of you have not seen any of this material before. We saw in the previous talk that physics is concerned with computations of such integrals. This comes from the fact that the integral kernel describing unitary evolution has matrix elements, which are integrations over, they're basically weighted averages of these over all possible paths with fixed boundary conditions, where each path contributes via its action, which is a real number, S of gamma. And the way that it contributes is by the exponential of I over h bar S of gamma, and so it contributes a unit complex number. And so you end up doing a undefined infinite dimensional integral of all of these complex numbers over the space of paths. Okay, so I want to give a highly simplified discussion, and so I just want to focus on this integral. And what we see here is that we have an exponential and the action. And I said that the action is S of gamma is an integral of the Lagrangian. And the Lagrangian is the difference between the kinetic and potential energy. And this kinetic energy is essentially, it's a quadratic function of velocity. It's basically x dot squared. So if this was a free particle, then we wouldn't have any potential energy, and we would only have this squared term. And so the simplest physical theory is one where the forces are not present, the external forces are not present, and the only type of energy that is present is the kinetic energy, and that's usually a square quantity in terms of the coordinate on the tangent bundle. So this is the reason why, in the extremely simplified discussion I'm going to do, I want to focus on integrals of the form e to the x squared, something quadratic, exponential of something quadratic. Okay. Now, whenever you are faced with this, well, okay, I mean, the way that I've written this, if I have to decide what the contour of integration or the domain of integration, if I go from minus infinity to plus infinity, then this is not going to look very good. But if I change the sign of x squared, this will look very good, and this will be a completely convergent integral. So I'm integrating the Gaussian. And this integral is the square root of pi. That's step one of learning how to do quantum field theory or quantum mechanics even in terms of path integrals. So let me build from this. So actually, why is this the case? Why is this integral square root of pi? The usual trick that you are taught is to square the left-hand side, and then you can convert this. So if you square this, you'll get an integral e to the minus x squared, and then if I use a different dummy variable for the second integral, it'll be e to the minus y squared, and it'll be an integral over the xy plane. Okay, and then that, if I multiply e to the minus x squared by e to the minus y squared, we can use the fact that this is a product of exponential is an exponential of the sum, so it'll be e to the minus sum of squares, x squared plus y squared, and that is in polar coordinates r squared. So we could change to polar coordinates and say that this is an integral from 0 to infinity of e to the minus r squared times r dr d theta, okay, and so then you can convince yourself, you can do those integrals, and you'll see that you'll get a 2 pi from the theta integration and a 1/2 from the radial integration, and so you'll get pi as the square of this integral, and so the integral of the original integral will be square root pi. So from this I can, let's say if I ask this question, I'm just going to start with this basic piece of information, and I'm going to build from there. So let's say I ask, what's the integral from minus infinity to infinity of e to the minus a x squared for a positive number, positive real number, then I can absorb a into the definition of x. So I can change my variable of integration to be x tilde being x times square root a, and then dx will be dx tilde divided by square root a, and so this will give me the square root of pi over a. Hopefully that's clear. Okay. The second question will be this. So suppose I do e to the minus a x squared plus bx plus c dx, minus infinity to infinity. Okay. Then what does this function actually look like? So the original Gaussian goes up to 1. This is e to the minus x squared. And so what is this? So if I take this a x squared plus bx plus c, then I can complete the square. So I could write it as Yeah. So I've written it as a square. Okay, so this means that the middle of the Gaussian will be shifted. So there's a minus of this on this whole thing, and so at minus b over 2a, I've got, sorry, my drawing is not that great. The Gaussian has been shifted and it has been rescaled, where at the middle, at the midpoint, it has height, which is given by this constant term. So it will be e to the b squared over 2a, sorry, b squared over 4a minus c. Right. So, okay, so what does this mean? This means that the shift by minus b over 2a, that is not going to change the integral. And this constant term, it's just scaling the entire integrand by a fixed constant. So the result will be, so this explains that the result of this integral will just be square root pi over a like before, because I'm doing minus a times a square. Okay, but the whole thing is being scaled by e to the b squared over 4a minus c. So this this is what we get as the second identity. Okay. Okay, and then the third step. Third step that I need is to increase the dimension. So let's say that now we go from dimension 1 to dimension n. Okay, and my integrand, the integrand is going to be e to the minus q of x, where x is a vector with n components, and q is a quadratic form of this form. Let's say 1 over 2 x transpose ax plus bx plus c, where c is just a constant. But let me write this out in detail. So this will be 1/2 x xi. Well, I don't know how you feel about index notation, but let me use it here. Plus b plus c. So A is a positive definite symmetric matrix, and B is an n-component row vector, and x is a point in Rn, let's say, and c is a number. Okay, and sorry, just by habit, I put a 1/2 here. Sorry about that. You see that there's a 1/2 here, whereas here I did not put a 1/2. If I put a 1/2 here, then my a becomes a over 2, and so this pi becomes a 2 pi. Okay, so what is this integral? This is an integral over Rn e to the minus qx. And this is going to be now dx1 dx2 dxn. Okay, well, the idea is that we can diagonalize this this quantity, this bilinear form. So in other words, we can think of this thing, we can do the same trick as here. We can diagonalize it so that it looks like terms like this, one-dimensional terms. And so the integral will be a product of n one-dimensional integrals. And so what is going to occur? So here I'm going to get, for each one-dimensional piece, I'm going to get square root pi over a. Actually, it'll be square root 2 pi over a because I have this 1/2. Okay, but a, what will a be? Well, a will be the eigenvalues of this matrix A, which I can diagonalize. Okay, and so I'm going to get a product of terms like this. So I'll get n copies of 2 pi, n factors of 2 pi, and n eigenvalues of a multiplied together. That product of eigenvalues is the determinant. So this will give me the square root of 2 pi to the n over the determinant of a, okay, multiplied by this thing here, which is the maximum value. Okay, and if I, the maximum value is you can figure out that it's exactly this you see how the maximum value is the the maximum value is the value of q evaluated at minus b over 2a. So in this case, it will be q evaluated at minus b minus a inverse applied to b. I prefer to write it in the other way, so put b b a inverse. And if I work this out, if I plug this in to this equation, I'm going to get oh, sorry, it's e to the, I'm sorry, it should be e to the minus q max, sorry. And so this thing here will be equal to oops, what is this? This will be equal to e to the minus this one is b squared over 4a, And for me, I have this 1/2 factor on A. So this is going to be for me B squared over 2A. So it's 1/2 BB with an A inverse as a matrix, and minus C. Okay. So if I write this out a little bit more pedantically, I'll write it like this: e to the 1/2 bi A inverse ij, the inverse matrix of A, bj minus c. Okay, let me rearrange this. To make it look nicer. Okay, that's our third piece of information that I'm going to need. Okay, so just to review, the integral of this Gaussian integral is giving me square root pi. This shifted and scaled Gaussian integral is giving me just a scaling shift of the result. So it's square root pi over A e to the b squared over 4a minus c. And then this is just an n-dimensional version of that. And you see basically that we have, an n-dimensional n factors, which look kind of like number 2. Okay, so please get comfortable with these calculations before going any further. This is the standard material about Gaussian integrals. And again, the reason that this is important is because in quantum mechanics or quantum field theory, we are computing integrals of the form e to the action, and the action is kinetic minus potential, and kinetic is squared expression. So it's essentially a Gaussian plus higher order terms. Okay, now the next step, the next tool, I just need to teach you some techniques. So those are some techniques, and the next technique that we need is we need to compute expectation values of functions using these e to the q quadratic exponential, these Gaussian weights. Okay, so what I want to do is compute something like this. So here I have an n-dimensional space. I have functions. One example of such a function would be the first coordinate multiplied by the third coordinate. So this is a quadratic function. Well, I mean, it's just a function on Rn. It's monomial. Okay. And I want to compute its expectation value. What does this mean? It means that I'm going to take the average value of this function weighted by the Gaussian weight. Okay, this by definition, this is the expectation value, and I want to compute this expression. Okay, I could put any function of the x's here. It's not important. I could put any function of x1 up to xn. I don't really care. I just want to use this one as an example. And what, so actually let me be a bit more precise. So what Gaussian weights do I want to consider? I want to consider q of x being 1/2 xi aij xj. Okay, so I just want a quadratic term up there. Okay, so let me write the numerator. This will be an integral of x1, x3, e to the minus 1/2 xi aij xj from minus infinity to infinity in all the variables. Okay, now here is the massive trick number one, which is that I'm going to, let me grab this thing. And let me introduce a complication. So this think of it this way, that this function, I'm computing this function, which is what is this? If I look at the left-hand side, what is this a function of? Well, the x's are dummy variables, which I'm integrating over. So the only thing that this is really a function of is the aij matrix. It's some number which is associated with the aij matrix, and the choice of this particular function in the front. Okay, but now what I've done is I've introduced a new quantity, a new parameter, ji. So this is a new parameter on which the function, on which the quantity I'm interested in depends. Right? I mean, originally this quantity that I'm trying to compute, it depends, what does it depend on? It depends on the function that I chose, x1, x3, okay? And it depends on what my weight is, and the weight is determined by this positive definite symmetric matrix. I didn't say that, but this A is positive definite symmetric, okay? But now I'm introducing an extra parameter, j1, j2, up to jn, and I have this dot product between j and the x's. Okay, and of course this is not equal to the left-hand side, but it will be if I compute the right-hand side and then set ji equals 0 for all I, then it will remove, by setting the extra parameter equal to 0, I will recover the left-hand side. So I took the integral I wanted, I made it more complicated, and then I simplify, and then I set the complication equal to 0. So of course I've done nothing in the end. Okay, but so this new parameter is, adding this new parameter is sometimes called adding a source term. So you should think that this is kind of like this is almost like I'm computing a certain expectation value associated to some particle, say like an electron, and then what I'll do is I'll turn on a magnetic field which wasn't there in the original problem, and I will compute the expectation value in the presence of this extra source, this new magnetic field. And then at the end of the calculation, I'll set the magnetic field to 0, and I'll obtain the result I want. Okay, so it's what appears to be a calculation, what appears to be a complication. But the interesting thing that happens is that if we now look at this this right-hand side, so now we compute the complicated integral. Okay, in here we compute this one, and we see that you see that here I have this jx term, and in front I have this x1, x3. So in particular, this quantity is the sum j1 x1 plus j2 x2 plus j3 x3 plus more. Okay, and so what you see is that one way for me to obtain this x1, x3 in front, I could express this in a slightly different way. I could say, suppose that I rewrite the integrand here. And if I were to put d by dj3 on this, then differentiating with respect to j3 exactly brings an x3 down in front of the exponential. So this is being exchanged with this. And then this x1, I can express it as d by dj1. Okay. So this is, you see how without adding the jx term, without adding the complication, right, and letting the problem depend on extra variables, j, this allows me now to use differentiation with respect to those variables in order to generate the terms x1, x3 in front of the exponential term. Okay, and because of the fact that the integral is so strongly convergent, I can easily take these differentiations outside the integral sign. So this is equal to d by dj1, d by dj3 of the integral that we already did. Okay. So because we did that integral in step 3 above, let's take a look again. We saw that the integration will give us 2 pi to the n over the determinant of the matrix. And then here I'm going to get e to the 1/2 b a inverse b minus c. And here I don't have a c. I have an a and I have a b. This is with the 1/2. I think I put a plus sign here. I could have put a minus sign, but I didn't want to get any signs here. So just be aware of that. Okay, so what am I going to get as my answer? Well, so I'll get, first of all, square root 2 pi to the n over the determinant of a. Okay, then I'll have this term, and notice that it's quadratic in b, so even if b has a minus sign, that minus sign cancels out. So I'm just going to have 1/2 j a inverse j. Or if I write it out properly, I'll get j I a inverse ij j j, sum over ij. And then we set j equals 0 at the end. So this is a remarkable thing, that we have no integration left. We did the integral. We just now have a differentiation to do. Right. So let's so that's where we are so far. Okay. So let me continue. Okay, and notice also that eventually I'm going to take this numerator and divide by this denominator. And this denominator is just this quantity here without the j, and it'll give me this as my answer. So this constant factor is going to get killed eventually when I divide by this quantity. The important thing is to figure out the j derivatives of this quantity here. Okay. Okay, so let me compute these derivatives. So if I take the j3 derivative, then what we'll see is that we'll get, for example, a Okay, so if I take the J3 derivative, then J3 is going to be multiplied with J1 up here. And if there is a J3, J1 term, there will also be a J1, J3 term, because this is symmetric. Okay, so both those terms will give the same result, and because of this 1/2, I lose the 1/2. So this represents two terms where I differentiate this with respect to J3. But of course, there's also a J3, J2, a J3, J3, and so on. So I'm going to get A3, 2, J2. Okay, that's the derivative, and then multiplied by the same thing. Okay. And then I'm going to have to apply del J1 to all this. Okay, so in computing this, let me move it over. Okay, so when I compute the J1 derivative, there's two possibilities. So either it will act, let me use a different color. So either it will act here, or, sorry, that was just a bad color to use. So when this acts, it either will act here. So when I differentiate this term with respect to J1, I will get A31. Or it could act here, but this would be 0. Okay, alternatively, and same thing with all of these terms, we just get 0. Sorry, what I mean is all of these terms here will all get 0. On the other hand, it could act on this term, and it will bring, so, and we will get more terms. So this differentiation kills J1, and it produces A31. Sorry, when I write Aij, I just mean A inverse, sorry, A inverse, the ij component of the inverse of A. Whereas the actual matrix entries, I'll just denote them with a lower index for A. These are the, let me write it this way. A is Aij and A inverse is Aij. It's a standard notation. Okay, so when I apply the derivative to this term, it kills the J1, and I obtain this constant. This, of course, will be multiplying e to the 1/2 j A inverse j. Okay, and this this differentiation this brings down a new term. So it will bring down it will bring down a 1 I j I. Okay, just like the first differentiation brought down this quantity here, which I could write it as A3 I j I, sum over I. Okay, and this new term here multiplies the term that was already there, a3i. I'll use a different dummy variable, 3j, j. So that's what I get. That's the differentiation, and this whole thing is the answer. So if I put j equals to 0, what you see is that this vanishes, and this just becomes 1. So what I get in the end is 2 pi n determinant a times a 3, 1. The 3, 1 entry of A inverse, of the inverse matrix. Okay, so the conclusion of this is that the expectation value of the x1, x3 function is a3, 1. All right. So it's kind of an interesting idea that you use a positive definite, or you use a symmetric matrix. I mean, you could see how you might do this for any matrix, but just for our purposes, we only need symmetric matrices. But you could kind of imagine that this is some kind of interesting phenomenon where you use the matrix A to define a function on Rn, which is this exponential function, e to the minus q of x. And then you might ask, well, if I have this function, how would I reconstruct A? How could I reconstruct the matrix A? And the idea is that if you use the coordinates, and you produce the monomials, xi, xj monomials, and if you look at their expectation value with respect to that probability distribution, e to the minus qx, the Gaussian probability distribution, you can obtain the entries of the inverse matrix. So it's a kind of it's a weird integral. It's like an analytical way using integrals to produce the inverse of a matrix. But anyway, what is going on here? Let's just kind of, I mean, I randomly chose this particular function x1, x3 to compute. So what is the general idea here? So in general, to compute if you wanted to compute the expectation value of some function of x times e to the minus q, then the trick that we're using is exactly to write this as to kind of convert this to a function, just take the same function but express it in terms of derivatives with respect to j of a more complicated integral, which is e to the minus q plus jx. And once you've computed that, let's say dnx, then just set j equals 0. So that's the first idea. That's if you want, this is the trick number 1. Okay, and then when we compute, okay, so then I just want to note, I just want to point out this combinatorial fact, and then note the combinatorial fact that each derivative d by dji, either it does one of the following things. So number 1, it could kill a constant. So for example, I mean, it didn't really occur here, but if we were to apply another derivative here to this expression, right, then d by dj2, let's say, would apply here and would kill this constant. And then it would act here, and it would, it would get rid of one of these j's, and then there would be another term here, and then it would bring down a j. So if I apply d by dj2, it could kill a constant, it could kill a j, or it could bring down another j. Those are the 3 things that it could do, and in each case, it just maintains the form of it being some like polynomial of j multiplied by the same exponential, which never changes. So it either kills a constant, it produces a constant, or let me say it kills a j in so it kills a j in these expressions that occur in front here. It could kill one of these, and that did happen right here, right? When d by dj1 acted here, it killed this j and produced a constant. Produces a constant. Okay, oops. Or it brings down a new j, or in other words, it creates a j. And this is all happening in front of the exponential. J A inverse j. Oh, yeah, right. With a 1/2. Okay, so okay, and so what does this combinatorial, what do these combinatorial facts mean? Well, in the end, j is being set to 0, and so anytime any j's remaining will be killed. Will not contribute. Okay, and so what does that mean? So you see here, the reason that we got a contribution was because d by dj3 brought down this term and created a j, And then d by dj1 killed this j. So there was a pairing that occurred. The pairing was that this operator, d by dj3, brought down a j in front, and this operator killed it. And it's because of this collaboration between these two operators that we got this constant. So, to get a contribution, a non-zero contribution, we need cooperation between a pair of operators, d by dj I and d by djj. Okay, this one brings down, creates a j, and this one kills a j. So first goes here, it creates a j, then this kills it, and we get a constant. That's the mechanism. Okay, so now let's implement this. Let's implement this this idea on a larger scale. So okay, so let's do another example. Okay, so idea number 2 is that we're going to use a simple diagrammatic technique to represent the combinatorics. So when I'm computing the x1, x3 expectation value, oops, what happened here? Yeah, okay, so the idea here is that I'm going to draw a dot for each of the external for each of the coordinates or variables. There could be, up to n. Okay, and we saw that the answer was A13. Or sorry, A31. It doesn't matter, it's symmetric. So I'll just put it like this. Suppose that we wanted to compute instead x1, x3, x4, x5. Okay, so let's just think about what this would entail. So here, what I have now are 5 variables that would occur in front here. And each of these 5 variables would be converted into a differentiation with respect to J1, J3, J4, and J5. And they would all be differentiating here. So I have 4 operators acting. And the first step is going to look exactly like this. When I apply the first step, I will get this J brought down. Okay, then the next operator will act. So d by dj5 will act first, and it'll give, so just, so this will be like d by dj5. D by dj4, dj3, d by dj1. And these are all going to act on this. Okay, and so right, and so you have to imagine what's going to happen is that this operator will bring down a j term. This operator will do 2 things. It will either kill that j, and in that case we will have obtained a pairing between these 2. But the other possibility is that it could bring down another j. Okay, so let me just work it out. So there will be sorry. Okay, so let me start with what's in front of e to the 1/2 j a inverse j. Initially, we just have nothing in front. Then, applying del j5, we get this in front. Then, applying del j4, there are 2 possibilities. Either I will get a5, 4, or I will get a new j that is created. Okay, so in this case, and of course these are added together. Okay. So in the next step, I'm going to have to apply del j3. Okay, so of course so in each case I'll get so either j3, so there's many possibilities now, right? So either this will differentiate this and give 0, that will not contribute, or it will bring down another j. So this term will go to I'm sorry, I should have let me just expand this out to, just in case someone is confused, let me put this all out. Okay, so now let's see how this looks. Sorry if it's obvious. I just wanted to. So if I now apply J3, let me write down all the possibilities. So either this is sent to 0, or we bring down a new J. Okay, so that's what happens to that term. Now when I act on here, there's several possibilities. There's 3 possibilities. Of course, I could bring down another J. That's one possibility. Another possibility, and these two are whether I differentiate here or I differentiate there. Okay, and all of these terms will be added together. At each level, it will be added together. So this will be A53, J3. Oh, I'm sorry. A53, that's the J3 derivative, multiplied by A4J. Or I could leave that one alone and multiply instead by A for 3 because I'm differentiating this term. Okay, so all these terms, actually let me circle them rather than put a plus between them. All these terms would be added together at the third stage, and then I have one more differentiation to do, d by dj1. Okay, now remember that at the end I am going to set j equals to 0. So you can see already that I've done too much work. Like, for example, this term here has so many j's that no matter how I differentiate this, there's always going to be a quadratic term in j left over, which is going to kill when j is equal to 0. So I don't have to worry about this term. I can kind of ignore, we can ignore this, since it goes to 0 when j is equal to 0. However, in all these terms, in these 3 terms, I will get something. So in this case, I will get an A54, A31. Here I will get an A53, A41. And here I will get an A51, A43. And so that is the answer. Okay, so I've just computed an integral, okay, in this way. Now, what I wanted to point out was how I would depict this diagrammatically. So let's do that. What I would draw is this. I would draw the point is that in order for these five to give contributions, they have to pair. You see here, look at this term. Look at this term here. How did we get this term? Well, there was a pairing off of 2 operators to produce the A54, right? Because I had to differentiate with respect to J5. That produced me the A5I. And then the derivative J4 killed that J. So I created J and destroyed with these 2 operators. And that gave me an A54. Okay, but that pairing had to be complemented by this pairing, the A3-1 pairing. Notice that I got this thing by by creating, from here, I created a J term using the d by d J3. So there was a creation of J and a destruction of J by the d by d J1. So this term here, if I write it out, this term occurs because del 5 and del 4 paired together, and then del 3 and del 1 paired together. On the other hand, this term occurred because del 3 and del 5 paired together, whereas del 4 and del 1 paired together. You see that del 4 created this term, and what happened here? 4, 1, 4, 1, and 5, 3, right? So yeah, so you see that 5 created this. Del 4 did not destroy this. Instead, it created. So now we're at the stage where 5 created and 4 created. And then we want 3 to kill what 5 created. So here you can see that 3 and 5 pair, and then 4 and 1 pair. And similarly, finally here, it's del 3 and del 4 that paired, and del 1 and del 5 that paired. So in other words, what you need to do diagrammatically is join these up in pairs in all possible ways. So in other words, one possibility is that 1 and 3 pair together, and in that case 4 and 5 would have to pair together. Or alternatively, 1 and 4 could pair together. Only 1, 3, 4, and 5 are occurring here, so the other points are irrelevant. If 1 and 4 pair together, then it must be that 3 and 5 pair together. And similarly, 1 could pair with 5, and 3 could pair with 4. And these are the only possibilities. These are the only possible pairings. And so we end up with 3 terms. This is going to be A13, the 1,3 component of the inverse, multiplied by A45. Okay, this will give me A14, A35, and this will give me A15, A34, and we have to add these together to get our answer. Okay, and notice that we have a situation where these are called 4-point functions. These are called 2-point functions. Notice that the 4-point function can be expressed in terms of products of 2-point functions. Okay, the fact. So there's you could call this a proposition that that the 4-point function, the expectation value of the product of these 4 functions is actually a sum of terms which are just products of the 2-point functions. This is called Vix theorem. In this setting. And I suggest you do some of these some of these calculations to get a handle for it. Okay. Okay, so now I need to bring in a new element. Maybe you should try to compute some. Well, okay, let me just make some comments. I'll stop this video and then I'll start another one, which will introduce interactions. So, so just to review, we started with the Gaussian integral, and we ended up with this expression for the general n-dimensional Gaussian integral. And then we saw that it's possible to compute expectation values for functions where we use this Gaussian as a probability distribution. And there's this very nice trick which allows us to complicate the integrand by introducing a source term and then representing the functions that we're interested in the expectations of as differential operators. Then we can compute the integral just as we did before, apply the differential operators, and set the complication to be 0. And what we end up with are the components of the inverse of the matrix A. And we end up with this combinatorial recipe for computing expectation values of functions, which you can amuse yourself to implement for other polynomials like this. You might wonder what happens if I square x1. Suppose I asked for the expectation value of x1 squared times x3 squared, suppose. Okay, but one thing I want to note is, that I picked a square, a degree 2 function and a degree 4 function. I did not pick a degree 1 function or a degree 3 function. The reason for that is because is clear, that in order to get some non-zero results from these differentiations, I need them to pair up, right? If I applied only one derivative, I would create a j, and then I would set j to be 0. And so there would be no contribution at this stage. Also, if I look at this stage, you see that every term, because of the fact that the parity is odd, will have a non-zero number of j's there. So if I set j to be 0 at this stage, everything will vanish. It's only at each even stage where I can possibly get something non-zero. Okay, let me leave it at that, and I'll continue in the next video. How do I stop this thing?